Astronomers have been using JWST for a few months now, and that's all great. But the question we always want to know is what comes next? And what will probably be next is some follow-on telescope that'll be about the same size as JWST, maybe called HabEx, maybe called LUVOIR. But what comes after that? There is a limit to the size of telescopes that you can build. It just gets more and more expensive to launch these things into space. And at a certain point, you'll reach the maximum size of telescope. But there are some really clever ideas on the horizon. One that I'm really excited about is called the Nautilus Telescope. And this uses a couple of really clever ideas. One is that it uses a flat lens. You're probably familiar with the Fresnel lens. Try scaling that up as a telescope lens. And the other idea is to launch a bunch of them, a constellation, a fleet of these telescopes working together, not as an interferometer, but just as the combined light of all of these telescopes. They would be relatively inexpensive to produce. You could launch 10, 15 of them at a time in a Starship. They would deploy out and you could just keep adding more telescopes to this giant array and maybe get to a point where you've got the equivalent of a 50-meter space telescope. Yes, please. So my guest today is Dr. Daniel Apai. He is the principal investigator of this concept, the Nautilus Telescope. He also works with NASA's Alien Earths project. He is a professor at the University of Arizona and has been working on this idea of flat lenses and the Nautilus Telescope for several years now. We did a video about 4 or 5 years ago about this, and it's great to see that it's continuing to be developed. So here is my conversation with Dr. Daniel Apai. So Daniel, I've been following the Nautilus Telescope for several years. We reported on it on Universe Today when you published a paper. I did a video about this. I did a series on like what comes after the Hubble Space Telescope, what comes after James Webb Space Telescope, what comes after LUVOIR. And I said your telescope was one of the telescopes that would be the next generation after LUVOIR. And then I saw the Nautilus make a round in the news again, and I was quite excited. I'm really glad to see this idea is still out there.
Thank you, Fraser. Thank you for following it. Yes, we are very excited about this project. So we've been working on for about 6 years on this project, and it's basically, as I said, it's a long-term project. The goal is to provide a technological option that would enable us to build much more powerful space telescopes than what we can do with current technology without breaking the bank.
Yeah, if you talk to the folks at like the James Webb Space Telescope, you know, to only be working on it for 6 years, that's nothing. You know,
That's right. Yeah, I mean, these are, space telescopes, space observatories are a bit like a cathedral, where sometimes even 2 or 3 generations of scientists may be working on them and developing different aspects and reaching. These are in many ways pinnacles of technological, development, really ambitious projects, and they do take time. James Webb, I believe the estimate is that about 10,000 people worked on and contributed to James Webb, and it was a project that lasted about 2 decades to bring to fruition. It's very exciting, but it's a major effort for pretty much humanity scale effort.
So let's talk about the Nautilus, because I think people are going to find it surprisingly different than any other telescope that they've seen before. So what is the basic idea of the Nautilus?
Yeah, so Nautilus looks completely different from any telescope that we have built today. And maybe it's worth exploring a little bit the context of why we think this is a good time for changing the paradigm before going into what the telescope is itself. So there are multiple processes that are converging in the current decade. And so one of them is that we have reached a point where arguably our technology with which we have been building space telescopes is plateauing. So we have, if you recall the Hubble Space Telescope, the mirror diameter, which is perhaps the most important parameter of a space telescope, the Hubble was 2.4 meters in diameter. And that was a system that was designed in the 70s, 80s, building on some existing technology. And then James Webb, which was basically designed and built over the past 2 decades, it's about 6.5 meters. So it's a little bit over 2 times larger. The next telescope that we are looking to build with the current technology may be just the same size as James Webb or maybe just a little bit larger. We just cannot really build significantly larger telescopes using the current mirror technology. And there are multiple reasons for this. One of it is that mirrors are very difficult to produce, very high quality mirrors. They're expensive to produce, to integrate, to test. So that's, in some ways, you could argue that the current technology is plateauing. At the same time, we, of course, are having discovered more than 5,000 extrasolar planets. We are all eager to explore these planets at greater depth and understand their atmospheres and then search for potential signatures of life in them. But that calls for much larger telescopes than what we can build.
Like the limitation, say, with the Hubble Space Telescope was what could fit inside the space shuttle. With James Webb, the limitation was what would fit within a 5-meter fairing of an Ariane rocket. And so much time was spent to make this thing fold like origami, and weight was shaved off of every single nut and bolt on that entire telescope to get it down to that weight. I mean, does the problem go away with next generation heavy lift vehicles like SLS or Falcon
exactly,
Heavy?
That's the third component that is converging here. Much larger rocket fairing and much greater capacity to low Earth orbit and beyond opens new sizes. And so it definitely drives down some of the implementations, like the Starship is projected to drive down the costs, the use of reusable launch vehicles to bringing up large masses to orbit. At the same time, the current paradigm, the cost scalability remains a problem. So just building a 2 or 3 times larger telescope, even if you can launch it, it is just going to be prohibitively expensive. So looking forward, we are basically a very exciting concept that NASA is pursuing currently, the Habitable Worlds Observatory, that is thought to take another 20-25 years to mature and launch. With about a similar budget, maybe larger than James Webb, and it is just not projected. We don't think that we can build a significantly larger telescope with that technology. People are looking into it, but it just looks very difficult.
And I mean, the other path to go is like to follow the route of the International Space Station, to go with space-based assembly of a larger telescope.
That's right. So there are a couple of groups one or two groups looking into that too, and that's also. I think that's also is an important direction to explore. There are certainly challenges in all of these, yes. I would say that we don't have, I mean, that direction is exciting also because it could benefit both from, human spaceflight, increases in human spaceflight capabilities, and also in-space satellite repair, assembly, and modifications, which is something that commercially and in the defense sector is explored very heavily. So there may be convergent technologies that may open possibilities there too.
But no matter what path you go down, there are all these exponential growth curves in complexity and expense to build a telescope, and even the ground-based telescopes, like the extremely large telescope at 39 meters is in the billions of dollars, which is vastly more expensive than any telescope that's come before that. And so you're just, to take this problem to space. It's still, I always think of an analogy of like the chip fabs that make the smaller and smaller microchips that we have today. They just, each one is an order of magnitude more expensive as you drop down to 5 nanometers to 3 nanometers. And that's down here on Earth. So I think that, and hopefully we'll get into this now, but like the thing that really excited me about the Nautilus is that you're taking a completely different approach in building a larger, more complicated, fancier telescope. You're kind of going,
That's right. Yes, exactly. So we basically about 6-7 years ago, I was participating in a small group of experts and we were brainstorming, and it became clear that we have a scalability issue, just as you described. I mean, as we go forward, how can we continue increasing the size and capabilities of the telescopes if the cost is an exponential factor? It just goes up much more steeply than the diameter of the telescope. And we are already basically pushing the limits. We are already building pretty much the most expensive telescopes that we can convince taxpayers to pay for. So how can we? And then there's also the other point that we didn't mention before, but it's related, that we build basically unique prototypes. So Hubble is a unique telescope. Spitzer is a unique telescope. James Webb is a unique telescope. And if any of these, they basically concentrate all our effort and work into a single example that concentrates also the risk. If any of these would not work, we would be left without those capabilities. I came to understand that actually James Webb, I used to think that if James Webb, something would happen to it, we could just build a second one because we already figured out how to build the first one. But it turns out that it's not the case. Many of the capabilities required to execute that project, to build, fabricate, integrate, test, those don't exist anymore. People have retired, moved on to other project facilities, have been repurposed and used for other purposes. So we looked at that too as an important component in the future of space telescopes, because we don't want to end up concentrating decades worth of resources, effort into basically a single example of something that could break. So that was kind of the motivation, that we said we need a telescope that has much more light collecting power. My personal drive was the science goal to be able to characterize 1,000 exo-Earth candidates atmospheres to search for signatures of life. We wanted to move away from the scalability challenges, and we wanted to move away from building single prototypes. So what we came up with, Nautilus, is what we can call a space telescope constellation. So the key idea is that instead of creating one giant telescope, we build a constellation, a group of space telescopes that can be used in conjunction to combine their light gathering power without forming an interferometer. And so these telescopes, as we imagine them, each of them would be very large, so they would be be larger, each of them, than James Webb. So we envision 8.5 meter diameter for them versus 6.5 meter for James Webb. But they would be replicated. So we are looking at an architecture where we would be launching a space observatory that has many identical components. And this basically means that we distribute at least some of the risks, we can distribute to many units. We can benefit from the economy of scale. And then it is always easier to build a fifth and the sixth and the seventh copy of something than building the first one.
So let's talk about the structure of one of these telescopes. So if you had one in front of you and you could walk around it and look at it, what would it look like?
Basically, what we looked at is creating a structure that can be launched in a compact configuration and then can deploy in space. We launch it in a compact configuration because a key part of this is that using something like a SpaceX Starship or the SLS B2, we could launch many units with a single rocket launch. And so we are not limited by weight, but potentially by volume. So we looked at a compact configuration. When it's launched, it could be like a cylindrical disk, a launch container that is deployed to orbit. And once it's on orbit, and this disk would be about 9.5 meter diameter, so it would just fit into SLS B2 or Starship internal the rocket fairing. Once it's in orbit, we would release gas from a gas valve, through a gas valve from a gas canister, and that could inflate part of the telescope, that it's an inflatable component, and that would emerge. We envision currently that it would be roughly spherical. You could think about a balloon, also it would be a thicker material. This is the inflation of that component. Is the purpose of that is to deliver the light collecting element to its location in the telescope in front of the focal plane, and that is really the magic component that we have been working so hard to develop, and that is a lens that I will speak more about. But once it's developed, the current design would call for basically something like a spherical. You could think about a large eyeball.
Yeah.
With on one end, basically this large lens.
Yeah, I kind of imagine like a beach ball with one portion of it has been painted silver. And so you have a stack of them, almost like the way the Starlinks are put inside a Falcon 9 today, and you launch a stack of these little shriveled up cylinders, and then they all get into space, and then each one inflates itself into a beach ball, and it's got a portion of its surface is a spherical mirror that is silvered and is. So that gets us the primary mirror. What do you do about like the secondary mirror?
So we actually have lenses. Yes. So when we looked at how to make this happen, that you have basically this replicated telescope system, what we found is that we are pretty good now as a community in replicating instruments, electronics, integrated optics. We have functional small sets that do exoplanet science, but we found that the most difficult part to replicate, and that often drives downstream costs, and I will get to this in greater depth later, is the optical system. So the conventional telescopes, cutting-edge telescopes too, almost all of them are using mirrors. So Hubble used the mirror, Spitzer used the mirror, Kepler, James Webb, of course, has the deployable unfolding mirror structure. So mirrors are used to collect starlight and then typically focus on a secondary mirror that then reflects the light back to an instrument package that is usually behind the primary mirror. That system, while it provides great image quality, but it is inherently very expensive to fabricate, to align, to keep in alignment, and to operate. So we said that we understood that we could not use a system like that and mass produce it. So what we have been working on here, the main component of our work has been to invent a technological alternative. And we are replacing mirrors with a special type of lens that has not been used in this form in the past. So right in the beginning of the birth of the telescopes, if you go back, the first telescopes were lens-based. And then there was a parallel evolution when early telescopes used sometimes lenses, sometimes mirrors. And the largest lens is about 1 meter in diameter at Yerkes Observatory, a classical refractive telescope. Lenses are working great in many ways, but they had one fatal flaw. And that is that lenses focus light through refraction. Basically, when light rays enter in a medium with a different optical density, they change their direction. And so you can basically create a shape made of glass where the light is refracted in a way that it enters the focus. But so what is important here is the shape. So if I want to scale up, because I want to collect more light, I want to scale up my lens by a factor of 10. Then it means that every direction I have to scale it up by the same factor. So its volume becomes 1,000 times larger and its weight too. So this weight basically was what killed the lenses, right? The conventional lenses just became so heavy that they could not be produced, they could not be kept in alignment, they were bending under their own weight. So we knew that mirrors are too expensive to scale up, lenses become too heavy to scale up. So we looked for an interesting solution that was invented already nearly 200 years ago for a different purpose, and then we moved from there. That purpose was, and here a French scientist, Fresnel, comes in. Fresnel was addressing a problem that was a major problem at his age, around 1780, and that was many ships were lost when they ran aground. So people, of course, installed lighthouses, but they didn't have an optical system that could create bright enough beams for the ships to be visible from great distances. So Fresnel invented a solution that we call now Fresnel lenses, and that really is a big family of optics. But the key thing is that it's a non-continuous lens. So what he did is basically he took a large lens, but he removed plane parallel chunks from the lens, basically pushing back each time the surface. And so he ended up with something like a sawtooth-like surface, which was, he lost imaging quality. So the images were not great, but they were excellent for a lighthouse. but the weight was much less. So he created these non-continuous lenses that were much more compact. So I knew about these lenses, of course, and most physicists study about this. We all love this. The question came up, could we go back to this old idea and then execute it with modern technology in a way that we recover the optical image quality that was lost? And so we were not the first one to think about this. There were two other projects, mostly defense-funded projects, that tried to do it, but they didn't have the kind of optical solution and know-how that we now have. And so I teamed up with and formed a team and have been working with optical scientists and James Wyant, College of Optical Sciences at the University of Arizona. I teamed up with a couple of colleagues, including Tom Milster, chief among them, who has specialized on using diffraction to bend light, creating basically these kind of surface features to bend light. And his work was focusing in the past on small-scale lenses. This is a similar challenge for microscopes. And he transferred that knowledge into large optics. So together with him, we invented a new type of lens, which uses multiple orders of diffraction combined together. In short, we are using supercomputers to design a fine pattern on the surface of lenses that bends the light into a focal point. And we use a complex pattern so that actually the images that we get are very high quality. Now, the key thing here is that the lenses can remain super thin. So they can be just a few millimeter thick and almost arbitrarily large. So that changes the whole scalability that I mentioned. If I now want to increase the lens by a factor of 10, it's not increasing in thickness, it's only increasing in surface area. So instead of becoming 1,000 times more massive, it becomes 100 times more massive. So that factor of a 10 gain over several orders of magnitude makes a huge difference in cost, fabrication, and execution.
Yeah, and I guess in the perfect world, if you were to like compare a flat lens against a mirror or a traditional glass lens, what, like, would it be on par, or would it be like 75% as good of of the same size?
Yeah.
Like how good do you think these flat lenses can get?
Yeah, that's a very good question. So the perfect maximum performance you could get from them, a parabolic mirror would give you the best performance. So our flat lenses can outperform conventional, even multi-component lenses, but a perfect parabolic mirror would be better. But the reality is that we don't live in a perfect world. Even James Webb's mirrors don't actually reach the perfect, image quality, and they are still amazing. So in practice, these systems that we develop, they have very high image quality, and you can configure them so they actually the ability to shape this surface with supercomputer gives you actually a great design freedom. So you can design very different systems, very wide field of view systems, very fast systems, very broad wavelength range. So there's the trade-offs. But we can design systems that are, for all practical purposes, perform as well as a mirror-based system, but they are much lighter, much cheaper to fabricate, and much easier to align and integrate. So as a system, while they perform similarly optically, but they could be basically much cheaper to build.
And I think that's the trick, because even if they are not as good, they're still so much cheaper to build to larger sizes that you sort of make up. Quantity has a quality all of its own.
Yeah, so it's a very interesting aspect of this, that if you look back at the evolution of the telescopes, right? I mean, there are different properties that we want in a telescope. And so maybe the most important ones are how much light you can collect and how sharp are the images. And then you may wonder, you may consider what wavelengths you want to use this. And so traditionally, when we build a single larger telescope than the previous one, then that gives you both sharper images and greater sensitivity because it collects more light. But it is much more expensive than building two smaller telescopes. So what we said basically here is that if our goal is to collect more light, we don't need to build one very large telescope, but we could build many smaller telescopes, if you like, and still gain basically the set from, the sensitivity increase, but not pushing for the sharper images that a super large telescope would provide. I would still mention that our concept is actually to build a larger telescope than James Webb, so our images could be sharper than James Webb, but we would not aim to have, say, a 50-meter diameter telescope that is insanely expensive and in practice not executable. So we kind of separate the sensitivity game from the image quality game.
And this idea kind of jumped out to me back when I first became aware of your work, is in launching multiple telescopes and then being able to have them collect light simultaneously from the same object, but not be an interferometer. Because I think that's what everybody expects, is that when you hear that you're going to fly, say, 5 9-meter telescopes in formation, that they're going to function as an interferometer. That seems like the natural thing that we do, but that adds a level of complexity to the system that might not be necessary. So you get the combined surface area of the multiple telescopes, but you don't get the increased baseline from their separation.
Exactly. So basically an interferometer, which is again, a really captivating and old idea, to launch telescopes and then basically combine light from them in a way that you carry the phase information of the incoming light waves, so they can basically work as one optical surface, if you like, and providing the combined not just the light, but also the spatial resolving power that you get from basically the maximum separation between them. It's an amazing concept, and our telescope in principle could be used to build an interferometer. But as you pointed out, it's an interferometer is very, very difficult to execute. So it becomes so expensive that we can achieve our science goals without that. So we are really looking at basically what is the way we can reach this really ambitious science goal while keeping the budget some consistent with what the telescopes that we have already built. An interferometer would have the added complexity of you have to basically keep these unit telescopes, finally measure the distance between them. So in terms of metrology, there are really significant challenges, and then you determine how much they drift potentially with a fraction of wavelengths and compensate for that. So it is just an optically, and in any way, any aspect, an interferometer is very challenging and expensive. And we found that we actually don't need it. If we go with basically using planetary transits, then using a temporal modulation to characterize the planets rather than spatially separating the light of the star and the planet, and we don't need that spatial information.
And so theoretically, though, once you've got, say, I'm not sure how many you were planning to hope to launch in one, but say you launch 5 in one launch, or 10, and then you launch 10 more, and then you launch 10 more, and then you launch 10 more, and they just keep piling up in this bigger and bigger constellation, and each one adds the surface area of the additional telescopes. And you're sort of inching your way towards a 50-meter telescope.
Exactly. So if you take the current volume estimates for the Starship, for example, we would expect to be able to pack in 12 to maybe 15 units, depending on how compact we can pack them. And so with 2 launches, we could actually build up pretty close to a 50-meter diameter equivalent, light collecting power. So which is, it's about a factor of 80 gain over James Webb light collecting power. And you could add with more launches, more of these telescopes. I mean, one of the beauty here is that this is a more resilient system. If one of these telescopes doesn't work, you didn't lose the project. If, for example, if there would be, like with James Webb, one of the big challenges was that the budget was, getting bigger and bigger and bigger, and you are at the situation that you spend 90% of the money, but you cannot launch a telescope that's 90% ready. You need to keep on adding money, and the costs just go up potentially.
I guess I want to talk about capabilities. So what does like, it just sounds ridiculous, right? What does a 50-meter space telescope get you?
Yeah, no, I think it would be pretty exciting. So you could do basically almost all type of astrophysics and planetary science that Hubble and James Webb can do, but with much greater sensitivity. So you would have this very substantial gain in the ability of looking for faint objects or collect light and take very, very high quality, for example, spectra of objects. But it would go more than that. So it could do more than that, because one of the big things is that you could use all of these telescopes to point to the same target, right? But you could actually don't have to. You could point them to different targets. So one of the, realistically the biggest limitation of James Webb and Hubble now is that at a given time, only one astronomer can use it, or one group of astronomers. It can only do one project at a time. And with this telescope array, you could use basically if you had 35 units, you could do 35 different projects. Some of these may use smaller groups. You could use maybe 4 or 5 telescopes to conduct a survey of the sky, or you could do just 35 independent projects looking from near-Earth asteroid, Kuiper belt objects, monitoring Jupiter, to look for supernovae and galaxies. You could also configure this array in a way that, for example, you would have a couple of telescopes that are searching for, say, new supernovae. And whenever you have a new supernovae, you could have a subset of the array, another part of the array turn there and collect light, immediate, transient follow-up. So it actually, the most obvious gain is from the sensitivity itself, but actually the shifting to this new paradigm would really enable you to think differently about structuring science programs and doing much more with the facility of a similar cost.
And so like an astronomer could get time on the array and say how many telescopes they need to make their detection, and then they could be tasked with 1 or 2 or 5 or the entire array if it's that urgent. And you could have a dozen different science projects going on simultaneously, which is
exactly. And you could dynamically reallocate telescopes too. If you find something interesting, you search for something, you find something interesting. Sometimes the photometric detection requires just one telescope, but then to get a high quality spectrum, you may need much more light, so you could turn the other ones there. And so I think it's a concept that is used in a couple of ground-based radio telescopes, where you have radio telescope arrays and you can allocate sub-arrays to different tasks. But it has not been used in space, and it would be, I think, a real game changer.
Yeah. And so, you're starting to explain some of the kinds of targets, but, you want to characterize the atmospheres of 1,000 Earths, for example.
Yes. So while you could do many things, I am the most excited about, and that's what drove, my work towards this idea, is to collect enough light so that we can study the atmospheres of about 1,000 exo-Earth candidates. So let me explain a little bit what we want to study and why 1,000 and what does it mean exo-Earth candidates. So as probably most of your viewers will know, we have discovered now as a community over 5,000 extrasolar planets, and the number keeps on increasing at a rapid pace. So that's very exciting. Most of these planets, however, we know very little about. So we know that they exist. We know usually what is their period, maybe what is their size and host star, but that's usually where our knowledge stops. It becomes really, really difficult to characterize what their atmospheres are made of, what is their climate, what is their history, what is their bulk composition. They just remain mostly inaccessible to us, even with the future technology. At the same time, we do want to study them more because we want to characterize planets that are increasingly similar to Earth. And we would ideally look for planets that we could call exo-Earth candidates, so candidates for being very similar to Earth in their key parameters. Once we have those planets, we would want to characterize them and see whether their atmospheres may be similar to the present-day Earth's atmosphere, or maybe the early Earths, the different atmospheric compositions the early Earths had. So we could test the hypothesis that some fraction, maybe the majority or minority of these worlds could actually have what we could call biosignature gases, so gases that could be clues to the existence of biology there. And the challenge is that, of course, planets, Earth-sized planets are relatively small as far as exoplanets go, because exoplanets are still difficult to find. Earth-sized planets are among the smallest ones that we can detect now in increasing numbers. But the atmospheres on an Earth-like planet is very tiny compared to the planet itself. So we are still speaking about a couple of percent difference. And so actually to detect and characterize the composition of the atmosphere requires you to basically look at different wavelengths and look for differences in the properties of the planet as a function of wavelengths. And so, long story short, you need lots of photons, lots of light to get those very small fraction of all the photons you collect that actually interacted with the atmosphere of the planet, so that they are influenced by the planet's atmosphere. So that's basically why we need large telescopes. What we want to do there is to characterize the in our case, the throughput, the transmissivity of the planetary atmosphere. So we want to look at situations where the planet is moving in front of its host star as a transit. And I isolate that small fraction of light that passes through the atmosphere of the planet. Those photons will basically carry the spectral imprints of the gases they interact with in the atmosphere. And in our specific case, the example that we go after is basically oxygen, molecular oxygen-free oxygen in the atmospheres of these planets. It's not the only gas we could detect, but the one that we use as basically as a guide for setting the performance.
So, I mean, that would be wonderful. I mean, we don't even know of any Earth-sized worlds orbiting sun-like stars in the habitable zone. So we have to find them first, and then we have to start characterizing them. And I mean, do you anticipate that there are 1,000 of these within a volume of space that is scannable by this next generation telescopes?
That's right. So we started with the project saying that our goal is to characterize about 1,000 exoers. So from there, we basically considered what is the state-of-the-art knowledge about the occurrence rates of Earth-sized planets in the habitable zones. We actually looked at different types of stars, but for sake of simplicity, let's go with sun-like stars. So what Eta Earth is, as it's commonly referred to. And then we considered how many stars you have per unit volume, say a cubic parsec. And so you can calculate what is the volume in which you will have enough stars to have enough Earth-sized planets that exist there. Because we are using transits, we can actually only see a fraction of those because we need a favorable star-planet alignment to us, which we consider 2. And so that means that you actually have to probe a greater volume. But then, we can calculate all of these for optimistic and pessimistic, assumptions, because there are some uncertainties in some of the many occurrence rates and types of planets. And then we actually decided the parameters of the telescope. So the diameter of the telescope is not it's not a chance number. It was determined, basically driven by these numbers to enable the 1,000 planets. So the telescope design is derived from that. And yes, and then we did cost studies to assess whether this is something that could be realistically built. So we did, and that's kind of an important technical and complex part of the how much does it cost if you never build it? How do you estimate it? So we had, and that remains difficult and uncertain. But we have done multiple studies, scaling from James Webb, bottom up, top down, different estimates, different assumptions. We actually ran thousands of models, realizations of the whole process, and we found that in a pretty large fraction of the parameter space, our costs would be consistent with the approximate cost of James Webb. So we think that there are good reasons to believe that this is possible to do. Of course, a lot will depend on technology development, how much we invest, what problems may emerge, as always with new technology. But given what we know, we are optimistic that this could be possible.
And what is the state of development today? I mean, you have tested out and developed lenses that you're quite happy with. I'm assuming that, I mean, you don't need to immediately launch a 9-meter telescope. You could make a smaller, like, would this work at a CubeSat level as a prototype? Would it fit on a Falcon 9?
Yeah, so it's a long path from going from an idea to a space observatory. And so we have been working initially on computer simulations and to figure out whether it would work as a simulation. So that we have done in the first year of the project, 2016, 2017. And then we were able to create the first prototypes that were about 2 inches in diameter or so, or 40 to
You'll
50
need a lot
millimeters.
of those.
Yes, and so that was basically just to try out the technology, these non-continuous surfaces. And that was successful, which was already an achievement because I had heard from quite a few people that this is impossible to do. And it was actually very rewarding when we had a system there and we could take a picture of, test objects, Air Force standard test objects in the lab and outside. And we could show that, in fact, it is working well. So we have patented this technology. And then over the past 5 years, we have been funded by the Moore Foundation, Gordon and Betty Moore Foundation, to increase the capabilities of the lenses. So we transitioned from the initial plastic lenses that we use for prototypes to glass lenses. And we increased the diameter by a factor of 5. So now we are building 10-inch or 240, 250 millimeter diameter lenses. We have demonstrated that we can create those. And these are not like handmade, ground and polished things, but instead we are using a key part of what we are doing. Why I didn't quite explain why it is cheaper, but it is cheaper because we are using a technology that was developed for mass production of optics. So my eyeglasses, most of the optics, the iPhone lenses, they are not ground and polished like mirrors are. They are basically molded and pressed in a master mold and mass produced. And so we basically took that technology and we are scaling it up. And we have been able to demonstrate that works not only for smaller optics, but in fact larger optics and even for these flat lenses. So we had put, my colleagues working on the manufacturing, they have been very successful with demonstrating that we can do these surfaces to a fraction of the light's wavelength precision, which is very exciting. And we showed that we can mass produce. So we actually have the capability now to basically, once we figured out the recipe, we can basically mass produce these lenses. So right now, in terms of where we are finishing the first 240 millimeter lens, which will be the world's largest precision molded diffractive lens. And we are building a telescope. In the next 2-3 weeks, we hope we will be able to complete it on Mount Lemmon, just outside Tucson, in the Sky Center, where we will be able to do on-sky experiments. We already characterized the lens partly in the lab. We will be bringing it to on-sky, so we'll be able to show that it works on the sky too. We are also planning to bring this to the stratosphere. So I'm in discussion with a company that is launching stratospheric instrumented balloons. And by doing that, we would be able to show that it works in near space environment. So that's increasing our technology readiness level. So we hope that in 2.5 years, we will be able to operate in the stratosphere and a balloon, doing observations from there. Parallel with that, we are also planning to increase the size of the lenses. We are working now on fundraising, basically finding support to increase the lenses by another factor of 5, the same scale, that the ratio that we have done. That would bring us to 1 meter size. So while that's not 8 meter, it would be a game changer already. So 1 meter size is basically the Kepler Space Telescope, Spitzer Space Telescope. These are really high impact space telescopes that had 1 meter diameter and sometimes a bit smaller optics, and we would be able to mass produce those. So we at that point, especially with the high technology readiness level that we are pursuing, we would be able to propose to NASA a spaceflight mission, and we would also be able to offer these optics to others. So ground-based observatories may use it, but the biggest game would be for space optics. So other groups are already interested in using our optics. So we are excited to see that work. I think that if we are able to get this other factor 4 or 5 in increase, we approach the 1 meter, it will be transformational for astrophysics and other sciences, because we would have mass-produced optics in a much lower cost and easier to test, integrate, and operate system than the current technologies.
Yeah, I wonder, even like at a consumer level, like, could I get a telescope with one of these lenses in it? Would it be less expensive to stamp out a 240 millimeter lens? I mean, that's about like an 8-inch. Yep. That's about a 9.25-inch telescope, right? That's a $2,000 telescope if I want to, with a nice mount.
That's right. So I see there is a point at which basically these systems will become cheaper and easier to produce than mirror-based systems. Exactly where that tipping point is, if you like, or break-even point, we are looking into, but it will depend on it depends in large part on how many telescopes we won't be doing that, but if there are, parties interested, this is definitely a potential option. As always, if you generate the large numbers, then this could be probably, cheaper and easier. In small numbers, it would be still expensive because it's an experimental technology. So somewhere there is a break-even point. I'm pretty sure for space optics, going beyond about 0.5, 0.6 meters is we believe it's really where it starts to pay off to use this technology, because for smaller optics, there are ready solutions. For the ground, the calculus is a bit different, and we haven't studied it really in great details, but you're right that I think there is a potential there too.
Yeah, wherever at a certain point, it's the mount that's the expensive part of the telescope. But as the telescope gets really large, then you need a mount that is really overbuilt. And if the lens itself and all the optics are lightweight, then perhaps that allows you to use a lighter capacity mount for a bigger lens. Yeah, that's interesting.
You have a benefit from basically mass producing the optical element, the lens versus the mirror. You have a benefit from a lighter optical system. So our lenses enable a much lighter system. Another thing that we didn't mention, but it is significant, is that the lens-based system is easier to align than a mirror-based system. It's easier to keep it in alignment, in focus. And so that translates to actually, less stringent requirements on the whole optical telescope assembly. So there's a reason why we don't use, reflector glasses. Almost all the consumer electronics is lens-based because it's much easier to work with lens-based systems.
Yeah, anyone who's ever had to collimate their telescope, when you have to fire the laser down and try to get the lens back in order, I really like refractors for that reason, because it's really simple to use the telescope. You don't have to make sure that its optics are all lined up. It just works, and that would be sort of exactly in that same vein. So, what's your dream? When do we see one of these go to space, do you think?
So it's. I think that it always depends on funding, and but I do think that this is something that within 2 decades we could build an array in space of medium or large telescopes. So that would be the ultimate goal, I think, to see something like a flagship scale, the Nautilus Space Observatory. But I think even before, I would be pretty happy to see in the next 6 years a small explorer or medium explorer mission in which we could fly, say, a 1 meter or a 1.2 meter diameter telescope, or perhaps a small constellation, to demonstrate that we can actually create 2, 3, or 4 replicas of the telescope. So I think that would already be very exciting to see.
That's awesome. Well, Daniel, it's been a pleasure to talk to you. If people want to keep track of the Nautilus Telescope and the other work that you're doing, what's the best place to do that?
Thank you, Fraser. It's been great to be here. I think people may follow. I sometimes tweet about our progress, so I think maybe that could be a disappearing venue, but I'm still using it. I will probably switch to something in the future. We also, from time to time, we have press releases, so there's some press coverage over our project, and we have a website too where we post things.
Yeah, we'll put a link to the website for
sure.
So
I think just googling Nautilus Space Observatory, can.
Well, I will be watching the development with great interest, and we will definitely be reporting on it more with Universe Today, and definitely keep us posted as you get a chance to actually launch on a balloon and eventually get a chance to go to space. I cannot wait for a giant constellation of 9-meter telescopes operating. That sounds fantastic. Thanks, Daniel. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltonan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.